Alright, so in this particular lab, I will be talking about propensity score matching in the survey data analysis context. If you are not familiar with propensity score, maybe take a look at the webinar that was posted couple days ago, and that will give you a very brief introduction to propensity score matching. And now I am going to present about propensity score matching in the survey data analysis. Alright, so in this particular lab, this is going to be a continuation of the previous lab. So here I am still using the CCHS123 combined dataset, and this particular R data file was saved from the first part of the lab. And we are still going to use the Analytic 11N dataset. Just for reminder that Analytic 11N dataset is basically a subset of the combined dataset, where we are only concerned about cycle 1.1 and northern province subjects, so that we have small sample size, so that we do not need a lot of time running this test lab, right? Alright, so this is what the dataset looks like. You have this CVD or cardiovascular disease, age, sex, marriage, education, income, all of these other covariates. I have created a ID variable. This is the weight variable, this is the cycle variable, and this is one miss variable that I have created earlier. Alright, so it is important that I do not have any variable named weight or weights, because the type of analysis that I'm going to do now, it will create a weights variable in the dataset, and it is probably a very good idea to change. If you have a weight variable, that means your body weight, maybe change that to a body weight variable. If you have a survey weight, maybe change that to a survey weight variable, so that we do not later forget which variables we are using, whether that is some other weight variable or this particular survey weight variable. Because if you mess this up, if you forget which particular variable is your survey weight variable and plug in a wrong survey weight variable or a wrong weight variable, then it can pretty much destroy your analysis. So it is very good idea to give it a proper name, so that you can later remember which weight this particular column is representing, and do it for both of the datasets. In this particular dataset, I not only have Analytic 11N, I also have the original dataset where no person was deleted, so that I have the original weights. Alright, okay, so in the class I will discuss about the propensity score analysis, but here is the brief discussion of propensity score analysis in terms of the steps. In the first step of the propensity score analysis, we need to have a model specification. So in here I am going to define what is going to be my exposure model or the propensity score model, and OA is going to be my exposure variable, and age, sex, stress, and whatever variable that I have as a confounder, those variables are my adjustment variables. And I also have a list of covariates, all of the same list, and I put them in the var names, and I will need that later on. Alright, so to fit the propensity score model, I need to use the matchit function from the matchit package, and there are some specific arguments here that you can see from the website. Say for example, if you go to the website, you can see what are the different arguments, what does this model means, what does this discard mean, what does this replace mean, and all of this description you can find in the R documentation. Alright, so first we have already decided what is going to be our exposure model, right? In the second step, we are going to match by the propensity score that I generate using this particular formula that I have decided in the step 1. So now I'm in the step 2, and I am telling this function to use the propensity score formula that I have defined, use the data file, not the design file. And I am also defining my methods as the nearest neighborhood method, and I am defining the ratio as 1. That means I want pair matching using the nearest neighborhood algorithm, using the data file, and using this particular formula. And it is always a good idea to set the seed before you run this matchit package, so that you can reproduce your own result. When you are running it second time, you can get the same result if you set the seed. Otherwise, by the nearest neighborhood algorithm, if there are two matching that are possible, it will randomly pick one, and that's why you need this randomness check by setting the seed. Alright, I am using the matchit function, and I created this matching object, and this matching object is very important in the sense that it will give you a sense of how many subjects were matched, how many subjects were not matched, right? So your ratio was 1 to 1, and you did not really have a lot of subjects. That's why you are getting exactly 1 to 1 pair matching using this nearest neighborhood algorithm. And once you do your matching, you can extract the data using the match data function, and then see what was the original dataset. The original dataset was more than 1400, but after you do the matching, 67 plus 67, it is going to be 134 subjects only. Alright, so in the next couple of steps, these are not really essential, but it is probably good to know that if you are using the match matrix, you can extract exactly who was in the matched data, and then you can also extract who were your treated subjects, who were your untreated subjects by using these commands. And you can also try to extract the matched treated data, and you can also try to extract the matched untreated data. So everybody here is O equal to 0, and everybody here is O equal to 1. Alright, so instead of going through all of that, you can simply use the match.data to extract your whole data set. You do not need to see these IDs. You can check who is matched with whom, but that does not mean that you need to check them. Alright, so in here, what I am trying to do is I am trying to find out the two persons that were matched in the first pair, say for example. So you can see in these two datasets or two observations, one was not treated and one was treated, because OA is our exposure variable, right? And these two were matched. So this is the propensity score for the control patient, and this is the propensity score for the treated patient. See that our distance, we are getting a match who is 0.18 far away, scale far away from the control patient. And see Weights is something else that this package directly created, and for pair matching it does not have a lot of meaning, so we are going to omit this for now. And these are the matching ID. That means that within ID1, within the first pair, we are matching these two control and treated. Right. So for in terms of other variable, let us take a look at the other variables briefly. The survey weight variable was not matched, but the immigration variable was matched in terms of propensity score. So not immigrant, and then fruit, you see some of one in the control group it was 0 to 3, but in the treated group it was 4 to 6. That means we are not going to get exact matching, but overall covariate distribution are going to be somewhat similar. So for example, in here smoking was never smoker and current smoker and things like that. Physical activity was similar, but you will see some of the variables differ to some extent, right? So it is not going to be exactly similar to the exact matching that you have seen earlier. The only thing that we are matching here is this distance or the propensity score. So by distance, it means that these are the propensity scores, and we are matching with respect to the propensity scores using the nearest neighborhood algorithm, where some of the covariate distributions are not going to be exactly the same, but in general the covariate distributions are somewhat similar. Say this is the second pair, so ID equals 2, matching ID equals 2. This is the second pair, no event, married single, non-white white. So there are some differences in there, but in terms of the distance, you can see the propensity scores are very similar, 0.06, 0.01, right? So that is the main idea behind propensity score. We are only going to be matching with respect to this propensity score, but we are not going to look into all of the single detailed values of them, even though some of those values can be similar. All right. So now we are moving on to the third step. Remember what was in the step 1? Step 1 was we defined the exposure formula. In the step 2, we have used the nearest neighborhood algorithm to do the matching, right? And in the third step, we are going to assess how good was our match. So there are some graphical plots in the match it package. So you can see some of these are unmatched control, and these people were matched. So you can see there was one person here in the control unit, but there were couple of subjects who were not necessarily very close to the control unit, right? All right, so with respect to the raw histogram of the propensity score, you can see that these look slightly different, but in terms of the treated, you can also see there are still some differences even after matching for the treated and control units propensity score. All right, we can also do the absolute standardized difference in means plot checking. So this is in the original dataset, and this is in the matched dataset. You can see everything is below at least 0.5, which is not good enough. Maybe we could go a bit lower, but let's see. We will see what was the SMD in particular. We can check the overlap. Generally speaking, I would say there were some overlap, even though after this, say for example 0.57 or something like that, there are no overlap, right? So these patients will not be will not have overlap. So there are some other packages that you can use to get this kind of plots directly. See, you have to write a lot of codes to get this plot, but in Cobalt package you can simply use this function val plot, and that will give you this plot directly. And if you look at the data set, you can see this distance data set is going to be our propensity score variable, right? let us take a look at some of the numerical summaries of the propensity scores. It varies from very close to 0 to 0.6. Why? Because this propensity score is basically a probability, right? And you can cross tabulate with respect to the exposure variable as well. Alright, so after viewing the plot, do you think it is a good match or not, right? So still I think there are some more rooms for improvement, and that we can do by using by first checking whether how bad our fit was or how good our fit was, right? Using this create table 1 function. Remember that I'm not using the design, I'm just using the matched data. And see the SMD, some of the SMDs are greater than even 0.25. So even if you are considering SMD in a relaxed way, the highest SMD could be 0.2. In general sense, in the literature you will see that is considered as most liberal SMD cut point. Some people also use 0.1 as a SMD, and that could be in that 0.1 category. Even there are some more variables that would not make that cut point, right? So these all would not make the cut point of 0.1. This is 0.2, even 0.1. Right, so there are other kind of balance measures. So instead of checking one SMD for all of the categories for a variable, you could check each difference categories SMDs as well, and you can also try to plot every single variable for the treated or the exposed or the unexposed category, and you can see more or less they look similar, but still there are some differences, right? Okay, so more or less I would say same. And also this is the laugh plot. Laugh plot is basically a pictorial version of this table that you have seen just here, right? So whatever difference adjustment you are seeing here for each categories, laugh plot is proposed by a biostatistician. I think his last name was Love, and this is the plot that we are getting out of plotting that, and you can see the 0.2 plus and minus are the cut points, and none of the points are there. But if your cut point was 0.1 here, then you would see some of the values would get truncated here. Alright, so how can we do better? We can try to add a caliper. So in the literature it was suggested that logit of the actually 2 standard deviation of the logit of the propensity score is considered as the suggested caliper. So what does that mean? In here, in the caliper, I am simply going to put this value, and that would mean that difference between the 2 propensity scores cannot be more than 0.233, right, when we are matching. So in that criteria you can see I am getting even less now. Now I'm getting 64 and 64 because remember there were some patients who were far away in the control group, in the treated group rather than the control group. So there are 3 patients who did not make the cut, and we have these cross tabulations, and we have this table 1 where I stratified by OA, and you can see still there are some variables that did not make our cutoff, even 0.02. So what do you do in that scenario when you're obviously this SMD is not satisfactory in the sense that it is not less than 0.2? So the general strategy is to go back to the step 1 and then try to figure out whether there is any interaction necessary, whether there is any polynomial necessary. For our case, we are dealing with some categorical variables, and the polynomial of categorical variable might not make a lot of sense, but the interactions might still make some sense. So if you think of some interactions that are biologically plausible, you can try to include those interactions in the step 1 and then repeat step 1 to 3 to come back to this step where you check the table 1 for this matched dataset, and you try to see whether your SMDs went down or not, right? So that is the first strategy you should take. You should change your model specification in step 1 and then come back again after changing this model by maybe including some interaction terms, and if there were some continuous variables, maybe you could try to include some polynomial term. If you plot the residuals for this regression, you can try to see whether there was any curvature that you can see. Unfortunately, when you are dealing with logistic regression, there are some curvature that are inherent. So finding the polynomial effect or whether we need to include a polynomial in the logistic regression is not that easy, but certainly we can try to include some interaction terms to try to improve the SMDs in here. So that is our goal. We are basically trying to improve our SMD in such a way that our SMD is less than a certain cut point. It could be 0.1, it could be 0.2, but you have to decide that before you make the analysis. All right, so say we are at a stage where we repeatedly modeled and we got all of these SMDs less than 0.2, which is our predefined cut point. If that was the case, then only we move to the step 4. And in this step 4, you can see I'm just using the matched dataset to get the odds ratios, right? But generally speaking, when you are estimating the treatment effect from the matched data, you are supposed to use design instead of the matched data only. Otherwise, your mapping from sample to population will not happen. So in the step 4, you need to consider the design. So for that design, you again try to create a matched variable, and based on that matched variable, you try to subset the dataset that we have done in the previous lab as well as in the previous lab. And then in the matched dataset, if you want, you can try to check the balance, but balance is usually not checked in the design. Balance is usually checked in the sample matched dataset. So this you can obviously check, but this is not something that we want to do. What we want to do is that using that design, we want to check the crude association in the matched dataset, and in the matched dataset the crude association was 0.76, right? Okay. All right, so that brings us to some of the more advanced options that we can use in the match it package. We have already used a caliper close to 0.23 previously. Let us just work with 0.2 here, and we are now moving away from the pair matching. We're doing a 1 to 5 matching. So for each treated, I want to get 5 control subjects because I have many control subjects in my dataset. That is something I can do. So you can see now I am getting more and more subjects. I still am losing a lot of patients, but from before, when I'm using 1 to 5 ratio, I'm getting more and more subjects. And once we get that, I can do this create table 1 again to check the table 1 function. And now you can see none of the SMDs in here are greater than 0.2. So this one is not greater than 0.2, and you can go down and you can see none of these are greater than 0.2. So you see you can improve balance by increasing the number of controls in your dataset as well, such as in this particular example. And you can try to look at the dataset. One thing you should notice here is that previously, so these are the survey weights, right? These are something different. These are something that we used in our survey data analysis. But there is a new variable, weights, and previously it was all 1 when we were doing the pair matching. But as soon as we are moving away from pair matching, we can see the weights are slightly different now, right? Okay. So how do we really work with these type of weights? So to incorporate these type of weights, what we need to do is we again need to go back to the design object, and we are using the analytic miss entire dataset to create that design object, and we will have some of the matched dataset, as a subset, right? And in that subset you can see the odds ratio is 0.83, and in this particular analysis I did not take into consideration of these weights, and these weights are basically matching weights, right? Okay. If we want to take into account of this matching weight, which would be the better way of doing analysis, then what we can do is we can multiply the weights with the survey weights to get the new weights for the design that we will create. So we are using these weights and the survey weights to create the combined weights, and we are using that combined weights to create our design object now. So what is this combined weight? This is the multiplication of the matching weight as well as the survey weight, and we can also subset this data based on who was matched and not, and then we can do the analysis and see now the odds ratio is different. Now the odds ratio is 1.1. So that means what? Having the osteoarthritis is a risk factor for the cardiovascular event, even though this is not going to be significant, but at least we can see some harmful impact in here. All right. So not only we can do 1 to 5 matching, we can also try to do matching with replacement. That means same control subject can be chosen for multiple treated subjects. And it was shown in the literature that if you do this with replacement, then there are some desirable statistical property. But the problem here is that as soon as you use more ratio and as soon as you use with replacement, you will see that the weights variable, the matching weights variable, will be different than 1. That means what? That means that you say, for example, in here, so these are the survey weights and these are the matching weights, and you can see the matching weights are not always 1. That means you need to take this matching weight into consideration, right? And look at what we got here. So you can see none of these SMDs are greater than 0.2 when we added not only 1 to 5 ratio matching, we also added the caliper and we also used the with replacement. But as a consequence of using these advanced options, we are getting these matching weights that we need to take into consideration. So similarly, we can create the combined weight and then use that combined weight to create our design, and then subset based on who was matched and who were not, and then that will give us the odds ratio, which is 1.4. One can wonder why our odds ratio is so volatile. Sometimes it is 0.76, sometimes 1.1, and now I have 1.4. That is because of the small sample size that I'm dealing with here. So couple hundred is usually not enough to get a very good estimate of the odds ratio. The other point is that I am not really adjusting for any other covariates here. Generally speaking, only matching, even if it is propensity score matching or exact matching, only matching is not enough to get rid of all the confounding. Generally, some combination of matching as well as covariate adjustment in the outcome analysis here would be desirable to get rid of or reduce the amount of confounding. Alright, so in this particular lab, what we have done is we have used the CCHS dataset, where since we are using only the public version of CCHS, we are only using the weight, but there are other survey features such as the strata and cluster, which are not available in the public version of CCHS. So for that, we are going to use the next lab, where I will show you how to use NHANES dataset, because in the NHANES dataset they give you some masked version of the strata and cluster, and you can use the full functionality of the design survey design function in the next lab.